In the last class, we have gone through a scheduling algorithm which is called first come first serve FCFS, which is a scheduling algorithm. And today we'll see another scheduling algorithm which is a better version of it. So what was the problem in the first come first serve? That is Convoy Effect. What is that Convoy Effect? The Convoy Effect is is telling us that if a bigger program come into the system, so smaller program has to wait for a longer period of time. So to reduce that type of problem, another algorithm has been shown up which is called shortest job first. Means if 3 or 4 or n number of jobs are there ready to run, so we are going to pick up any one of the process with least burst time. So that was the idea behind the shortest job first. So let's go and see that how this shortest job first is going to work. So in the shortest job first scheduling algorithm, it is associated with each process the length of its next CPU burst. Use these length to schedule the process with the shortest time. Now the idea behind it is that every process should have burst time, and that burst time should be known prior to its execution. So that is a requirement of shortest job first, that a process, if it is ready to run, then the scheduler should know that what is the burst time of each and every process prior to its execution. So because it is in the ready state. Shortest job first is optimal, gives minimum average waiting time for a given set of process. So if we have a set of processes, so SJF is optimal, then first come first serve. The difficulty is known, the length of the next CPU request could ask the user. So the reason behind the difficulty to implement shortest job first is only one. And what is that? Is to get the length, know the length of the next CPU request. So we don't know that how much time it is going to take. If we don't know, then it will be very difficult to find out which one is a shorter and which one is a longer. So this shortest job first, there are the criteria you can see. In the shortest job first, criteria is burst time. So burst time is the criteria. If we find out that any particular point of time t, 3 processes are there, so which process has least burst time? If let's assume that if burst time is same for 2 or more process, then after that we have to look for arrival time. That is a working as a tiebreaker. So if burst time is same for 2 or more process, then we have to look for the arrival time. Like in a previous first come first serve, what was the criteria? The criteria was arrival time. And if arrival time was same, we have to look for the process ID. Whose process ID is less, we have to consider it. Now come to the mode. What is the mode of shortest job first? So here it comes into the category of non-preemptive. So it is also non-preemptive type of scheduling. So what is non-preemptive scheduling? The non-preemptive scheduling is whenever a process has been allotted the CPU, the process should execute all its instruction and then it will go to the termination state. So from the new, any process will go to ready state. From here it will go to the running state, and from running state it will go to the terminated state. So these are the transition diagram of any process of non-preemption scheduling. So we'll follow the non-preemption way of scheduling in shortage job first also. But the criteria to choose which process will go next, it is a burst time. If burst time will be the same for the shortest job available, then we have to look for the arrival time. Okay, so the arrival time is working as a tiebreaker. Let's see one example which is written here. So we have a process P1, P2, and P3 and P4. We have a burst time 6, 8, 7, and 3. And let's assume that arrival time of this will be 0, 0, 0, 0. It means at a particular time 0, all the processes are available in the ready queue or in the ready state. Okay, in the ready state, not in the ready queue, because queue is the data structure used in first come first serve. Now here we have the number of processes which are available in the ready state. It means that they are in the second primary memory, which is a RAM, which is in the RAM. So all these processes are inside the RAM. Now next is which one has to choose. So definitely if you'll go for the burst time as a criteria, so the first one that we'll choose is P3. So P3 will go first. So it is going first. Sorry, P4. It is P1, P2, P3, P4. So first one is P4. P4 will go first. And what is the burst time? Burst time is 3. So it will go from 0 to 3. After finishing, which are left? So we have P1, P2, and P3 are left. Which is having the least burst time? So definitely we'll find out 6 has the least burst time. So now this is going to get the CPU next, which is P1 of 6 unit of time. So it will start with 3, execute 6 unit, and complete the execution at 9 unit of time. Okay. Now which are left? So 2 and 3 are left. Which we have to choose? Definitely we have to choose the least one. So this will go the third trip is this. So the P3 will come here. The execution time is 7. So it will start with 9 and end with 16. Now after that we have only one left. So we can choose that. And P2 will come here and the execution, the burst time is 8. It will execute from 16 and it will end at 24. Now let's find it out different timing or different time related to a process. So what are the different time that will go? So the first time that we'll see here is completion time. So what is the completion time of P1? So the completion time of P1 you will find is 9. 9 is the completion time of P1. What is the completion time of P2? Is 24. What is the completion time of P3? You'll find it 16. What is the completion time of P4? So it is 3, right? Now after the completion time, we'll find out turnaround time. Now what is the turnaround time? Is completion time minus arrival time. So what is the completion time? Completion time is 9. Arrival time is 0. So turnaround time is also 9. 24 minus 0 is 24. 16 minus 0 is 16. 13 minus 0 is 3. So that it is same as the turnaround time. Now let's go to the waiting time. So the formula of waiting time is turnaround time minus burst time. So turnaround time minus burst time will do For the process 1, burst time is 9 minus, burst time is 6, turnaround time is 9, so 9 minus 6, it will be 3, is the waiting time. For the P2, you'll find it out that 24 minus 8 is the waiting time, so it will be 16. For process 3, it will be 16 minus 7, it will be 9, is the waiting time. And for P4, because P4 we have chosen at very first at time 0, so the waiting time is 0 here, 3 minus 3, turnaround time minus. So what is turnaround time? Turnaround time is completion time minus arrival time is my turnaround time, right? Now what is waiting time? Waiting time is nothing but turnaround time minus burst time. So in that way we have calculated all, and after that we can calculate the average waiting time and the average turnaround time. So what is the average waiting time here we have is 3 plus 16 plus 9 plus 0. So it will be 19 plus 9 is will be 28 divided by 4. Now average turnaround time will be 9 plus 24 plus 16 plus 3 divided by 4. It will be 33, then 36, then 52 divided by 4. So this is the turnaround time of the shortage job first with this particular example. Now we all say that the average waiting time 30. Okay, so we always say that shortest job first type of algorithm cannot be implemented. We cannot implement it in a real world. So this is not a practical algorithm. It is just a theoretical algorithm. Why we say it is not a practical algorithm? It is a theoretical algorithm because we know that to get the burst time of any process is not at all possible. Means we cannot know that how much time a process is going to take in the CPU to execute its all instruction. That cannot be calculated. Means overall burst time cannot be calculated. It is not practical. So practically we cannot calculate the burst time of any process prior to its execution. So if we cannot do that, then how, with the basis of burst time, we can have an algorithm which is called shortest job first. So that is not at all implementable algorithm. But yeah, theoretically to understand that how we can reduce the overall waiting time and overall turnaround time, we use this, or to reduce the convoy effect. Now here if you'll analyze, in the shortage job first also, we can have the problem of convoy effect. Convoy effect is still possible. What is the convoy effect? Convoy effect is if a longer process come before the shorter process, then shorter process has to wait bit longer, because shorter process is, let's say it is the burst time is 1 and the longer process burst time is 20. So unnecessarily of burst time of one process has to wait for 20 unit of time to finish the first process. To reduce the problem of this that we have seen in the first come first serve, we are thinking that shortage job first can remove these problems, but these problems cannot be fully removed. I'll I'll show you some of the scenario where it proves that the convoy effect is still there in shortage job first. There is no book which is claiming that the shortage job first is still existing. Sorry, convoy effect is still existing in shortage job first. So no book is claiming like this. But if you see some of the algorithm, it actually proves that convoy effect exists in shortage of first. Before going to the other concept, let's try to solve some more examples related to shortage of first. So shortage of first, we'll see some more example. Let's say we have process ID. We have arrival time. We have burst time. Okay. Let's say the process ID is 1, 2, 3, 4, and 5. The arrival time is also like the same 1, 2, 3, 4, and 5. And bus time is 7, 5, 1, 2, and 8. Okay, let's assume like this. Now, let's go to draw the Gantt chart. Now, we're starting the process at time 0, but there is no process in time 0, if you can see. The first process that has been arrived at time 1. So, a unit time 1, a process is arriving, so CPU is idle for 0 to 1 unit of time. Now, at first unit of time, we have only one process, which is P1. Now, because we have only P1 at 1 unit of time here, and we doesn't have any choice to actually calculate the least or the shortest job time or shortest burst time for the job. So we have to take P1 here in the consideration. And because is it a non-preemptive scheduling, we'll execute it up to 7 unit of time, means it will go from 1 to 7, it is completing in 8. Now if we'll see at time unit of 8, we have all the process which are available, means P1 is finished, we have P2, we have P3, we have P4, and we have P5, which are all are available. Now from these available processes, we have to choose the next. So if we'll see, so which one is the least burst time? So you can find it out that P3 has the least burst time of 1. So P3 will come into the CPU and it has the chance to execute. So P3 will execute, and because the burst time is 1, it will be 9. It will finish in 9. So P3 is finished. Which is left? So we have P2, P4, and P5 which are left. So P2, P4, and P5. Least one is this, which is P4. So P4 will get the chance to execute. It will execute at 11. Now P4 is finished. We have P2 and P5. If we see that P2 is 5 and P5 is 8, we have to pick up P2 because it has the least burst time, which is a 5. So it will finish at 16. Now the last one which is left is P5, and then the P5 will come here in the execution, and P5 is going to execute for 8 unit of time, and it will finish at 24. Two time that we have to calculate. So the first time is completion time. So what is the completion time here for different processes? So the completion time of process 1 is 8. Completion time of process 2 is 16. Completion time of process 3 is 9. Completion time of process 4 is 11. And completion time of process 5 is 24. Now, what is a turnaround time? Turnaround time is completion time minus arrival time. So it will be 7. It is 14. It is 6. It is 7. And this one is 19. So this is the turnaround time. The last one that we have to calculate is waiting time. Waiting time is turnaround time minus burst time. So it will be 0. 14 minus 5, it will be 9. 6 minus 1 is 5. 7 minus 2, it is 5. 19 minus 8, it is 11. So this is my turnaround time, and this is my waiting time. Now you can calculate the average waiting time and average turnaround time. That these two things you can calculate. So the average waiting time will be 0 plus 9 plus 5 plus 5 plus 11 divided by 1, 2, 3, 4, 5. Here we have 7 plus 14 plus 6 plus 7 plus 19 divided by 5. Okay. So this is how we can calculate the average waiting time and average turnaround time. Okay, now what else? Now I want to tell you about the convoy effect, right? So let's go to the example, another example of shortest job first, and try to understand the convoy effect. So we'll see shortest job first, and we'll try to demonstrate convoy effect. Let's see one example here. We have process ID, we have arrival time, and we have burst time. Let's say the process is 1, 2, and 3. The arrival time here is 0, 1, and let's say 2. Burst time is, let's say, 20, 2, or you can see 1 and 1. Okay. Let's see this. In this, how the shortest job first is going to work. Now we'll draw the Gantt chart for that. Now here in this particular example, you understood that which type of data structure we have to use. To fulfill the requirement of shortest job first. So the data structure, we cannot use queue here. Instead, we'll use here min heap. Now what is that min heap? We'll find out the minimum value at the very root and we'll delete it. So we'll take the minimum value at very root, and We delete it means we take that particular process into the CPU, execute it, and again find the minimum one, right? So min heap is actually going to work in this particular shortage of first example, in which first we supply all the process with the burst time into the min heap. Whatever we'll delete, we'll put into the queue. So let's say in the main heap, if we have arrival time 1 and we are using the min heap, so definitely we'll get P1 first because arrival time of P1 is 1. And after that, what is the minimum one is, if you'll go from here to here, so you'll find out the P3 has the minimum. So P3 will come after that. It has been given to the min heap. Min heap will generate the minimum value and will delete it. Again, the minimum value will come into the root and again will delete it. In that way, that minimum min heap is going to work. So whatever the ID, process ID we are going to delete from the min heap will come into the queue, and queue from the queue will pick up one process at a time. Right. So this is how the shortage of first algorithm is going to be implemented in a real program or in the real implementation. But as I told you, in a real life and in a real world, the shortage of first implementation is not possible. The reason is very simple. The burst time of any process cannot be calculated exactly before execution. So one process is executed, we know how much time it has been taken for the execution. Before that, nobody can tell that how much time it is going to take for the execution. So that's why shortage of first real-time implementation in such operating system is not at all possible. But it is a type of algorithm, that's why we are learning it. Let's go to the convoy effect and try to understand what is happening in this particular example. Now in this example, at particular time 0, at time 0, you will get it like only we have one process available, which is process 1 and having the burst time 20. So we doesn't have any choice to put process P1 into the CPU and it will execute for 20 unit of time. And after that, because we have done with 20 unit of time, we see that 1 and 2 unit of time is very less than that. So definitely they are ready to run. We have to pick up based on the burst time, because burst time is same for that. So we have to go for the arrival time, because arrival time is a tiebreaker. So the arrival time is 1. So we'll execute P2 after that with a 1 unit of time. And then P3 is going to come. We'll execute with 1 unit of time and it will complete at 22. Now here if we'll talk about different other times, which is completion time, turnaround time, and waiting time. So all these things we will just find it out. What is the completion time of P1, which is 20? Completion time of P2, which is 21. Completion time of P3, which is 22, right? Now let's go to the turnaround time, which is completion time minus arrival time. So it is 20. It is 20. And this one is also 20. Okay, let's go to the waiting time. What is the waiting time here is turnaround time minus burst time. So it is 0. 20 minus 1, which is 19. Here also 20 minus 1, which is 9. So what is the average waiting time? It is 0 plus 19 plus 19 divided by 3. Here we have average turnaround time, which is 20 plus 20 plus 20 divided by 3. Here it is 60 divided by 3, and here it is 38 divided by 3. This is the waiting time, right? Now, because of the bigger process which are coming before these shorter process, we are still having the convoy effect in this particular example. How we can remove the convoy effect? If we have these process ID, the arrival time and the burst time, if the sequence will be like this, as the burst time is the same, but the arrival time, the sequence of the arrival time will be different. Let's say it is taking 2 unit of time, it is taking 0 and it is taking 1. Then if you'll go for the Gantt chart again, you will find it out that here at time 0, P2 is there, it will execute at 1, then 1, P3 will come, it will execute at another 1, it will be 2, then at 2, P1 will come, then it will execute for 20 unit of time and it will end at 22. Now, if we'll calculate the different times here in this particular example, so what is the completion time? Here it is 22, here it is 1, and here it is 2. That is the completion time. Let's go to the turnaround time and waiting time. So here the turnaround time will be completion time minus arrival time, which is 20. Here it will be 1. Here it will be 1. That is the turnaround time. Now waiting time, here it is turnaround time minus burst time, it is 0. It is also 0 and it is also 0. So if you'll see here, the average waiting time we are getting here, it will be 0. And the average turnaround time that we are getting here, it is 22 divided by 3. And here you can see the turnaround time is 60 divided by 3. Here the average waiting time is 0. Here the average waiting time is 38 divided by 3. So you can see the process, 3 processes are there. The burst time is still the same. It's the same. This burst time and this burst time is the same. But the arrival time is different, right? So here it is arriving at 2, 0, and 1. Here it is arriving at 0, 1, and 2. That's all. The sequence has been changed, and the waiting time has reduced. So we can say that in all the scenario, or in each and every scenario, the shortage of first cannot reduce the problem, which is a problem of convoy effect or the starvation, that cannot be handled by shortage of first of the problem which are there in first come first serve in all the scenario. Because we have some of the scenario where if the arrival time is different, and let's say the longer process is get into the system previous to the shorter process, so the shorter process again going to be suffer. So to solve these type of problems, we have a solution which is called shortest remaining time first.